body in a image. So you can track the key points in the moving video or image to predict what activity has been taken place. For example, these days in watches and stuff. And next you have motion capture augmented reality, pretty self-explanatory. Again, training robots. Okay, robots also consists of joints, right? So you can capture images of robots or videos of robots, and you can pinpoint those key points in the robot's joints, and using those extracted key points, you can predict the end trajectory of the robot, the end point, the main contact point of that robot. Okay, cool. And lastly, we have motion tracking for consoles. So you have these just like Xboxes and connecting lots of these technology that use motion detection using these key points technique only to translate those key points into a model that is within your console. And now we'll describe the two in terms of approach of the problem. There are mainly two kinds of methods that you can do. One is bottom up, and then you have top down methods. Now in bottom up methods, what you do is you first calculate or find these key points which represent the joints in the body of the object, and then you use those key points to do further your classification or whatever regression, whatever task you have at your hand. And then on the contrast, you have top-down methods, which first find the features from the images, and then they use these features along with the bounding box to do your final downstream classification. So a couple of examples for bottom-up methods would be open pose and deep cut. And then you have top-down methods using RMP, alpha pose, and mask RCN. So what will be taking consideration would be these mask RCN. We'll be using these mask CNNs to do our downstream classification. So what our goal is to first we'll implement a mask RCN based pipeline to predict decisions given by the umpires in the cricket match by their actions, pretty self-explanatory. And then a very nice explanation of this could be automatic summary generation. So what you can perhaps do is take, so say a live streaming is going on, you can make a pipeline to detect what umpire is doing, and using those detections, what you can do is you can write a summary of the entire match on the fly. Okay, so let's talk a little about the main backbone of our projects. So let's say you have a classification task, right? So what you do is, generally what you do is you take a feature extractor pipeline, you pass an image through it, extract the features, patch another final classification layer on top of it, and train it using any loss, any cross entropy loss or class-based loss. Now, what if I say not only do you have to detect the object, you also have to detect where in that image is that object. Right? So now you not only have to predict the class, but also the position of the object in that image. So that position can be uniquely, can be determined by 4 points only, right? X, Y, W, and height. So XY would be the coordinates of the center, and W and H would be the width and height of that bounding box. So this is also pretty easy. What you do is instead of outputting K, where K is the number of classes, so instead of outputting K outputs, you output K plus 4 outputs. So first K of them would be your class prediction, and last 4 would be your XYZ and W outputs. Pretty simple. And you train first K with your cross entropy or any class-based loss, and last 4 with your any regression L1, L2 loss, right? This would work, whatever I said up until now would work if the image only has one object in it. You can detect that object, you can make a bounding box on that object. What if the underlying image has multiple objects in it? Then what would we do? So here comes the RCN, which tackles this problem only. So what they do is they first start with image. Now, the image that you'll be getting would have multiple objects in it, and all of these objects may belong to different category or same category or whatever may be the case. So what you do is you start with the image. First, you basically use a method called selective search to find the most probable bounding boxes, basically region proposals they are called. So what you do is take the image, use selective search to find region proposals These region proposals are the regions in the image that may correspond to some object. This is done. Selective search is a non-deep learning method that uses segmentation and that mainly uses segmentation to find these regions in the image. Now, each of these regions, so you have like 2,000 of these regions given by some non-deep learning method. Each of these regions is then reshaped into what do you say, common shape, maybe 5 by 5 or 7 by 7, and then this reshaped version of this image, this patch, a small patch, is passed through a CNN, and you do regular your classification and box regression. Now there's a problem in it. The problem is that there are like 2,000 regions, and so you have to do 2,000 forward passes and 2,000 backward passes, right, for each of these region proposal. Naturally, it is very slow. So next logical step would be to make it fast. How they do it is that now they do not do region proposal on the image, but they pass this image into the CNN and get these feature maps, and they do these region selection on these feature maps only. So again, they use something called region of interest method, which is again non-deep learning, right? So you have multiple patches of different sizes here. You just reshape those sizes to a 3 by 3 layer. This is fixed in this case, and then you pass it to fully connected layer to get your bounding box as well as your classification. So the difference would be here the image, the region of interest is found, you are getting these in the image only, and here you are doing in the feature space. Now this is very light space. You can see my okay. So this particular part of the pipeline is very light size, right? Only 3 by 3 passing to a 5 fully connected. Compared, so you're doing the big thing you're doing only once, and the small things you're doing multiple times. Where in this case you're doing everything multiple times. So naturally, this is much faster than your real RCNN. This is called fast RCNN, right? One thing to notice is this RY pooling layer. What it does is simply whatever size feature map you get, you try to snap it or crop into 3 by 3 so that you have 9 such regions, approximately square regions, to get 3 by 3. This is called RY pooling. That's all. From here, the next logical step would be to remove this, which is non-deep learning, to something that is again that uses deep learning. So this would be your faster CNN, even faster than your fast CNN. This will replace this RPN, this region proposal network, which was initially in fast RCNN, was just a non-deep learning method to give you out these regions, right? This is nothing. This is just a deep learning network which predicts your 4 coordinates some number of times. That's all. So each 4 coordinate would correspond to a patch in the feature map. That's all. So what they do is pass the image, get the features map, use RBN, use region proposal network to get some patches in the feature map, and do the same thing but slightly differently. Instead of using ROI align layer, they use they also do ROI pool only, right? No problem. So this is your fast RCN, which is an upgrade to fast RCN, which replaces this RPN, which basically adds this RPN. The final version of it ends up being your mask RCN, which will be using it. So the main changes are, first, this ROI align layer, which I'll explain what it is, and the next big change is adding this mask branching, right? So what they do is they pass the images, get the features, use RPNs to get these patches in the feature map, and then they use ROI align. In previous method, they use ROI pooling, right? And here they are using ROI align layer to reshape these patches into 3 by 3 final fixed size feature maps, and then they do masking and your classification and regression. This part is called the backbone, and the upper part is called head. Backbone could be any deep network. So some examples are like there is a 50, 100, and feature pyramid network, right? This is just a 2D version of that only. You take an image, you pass it through CNN, your region proposal network will predict your regions, which are to your importance, your ROI align layer. So once you propose the regions, your ROI align layer will convert those regions into 3 by 3 mask, which you pass 3 by 3 feature maps, which you pass through to do your like binary classification, binary cross entropy loss with mask, and your other losses cross entropy with classes, and your regression loss with your boundary box. That's all. How is this ROI align layer any different from your ROI pooling layer? Is this. So in ROI pooling layer, if you remember, you just try to snap these in roughly 3 by 3 squares. You just try to do it. Here what you do is you do floating point division to get to evenly divides these cells into 3 by 3 cells, right? So you may have some from some half of this cell here and half of this cell on the other side. Next, for each cell you sample 4 points which are equidistant to each other, right? And whichever cell this point lies onto, you take the value of that cell and write it here. Similarly, whichever cell this cross lands to, you take the value of that cell and write it here. So you'll have 4 such values, and then you do max pooling on that 4 values only. Cool. This is what ROI align layer does. So this was the basic architecture about the history of the architecture and how it has evolved, right? Next would be our dataset exploration. So the dataset that we use is handpicked. So both of us have like gone out and collected these datasets from mostly from Getty Images only, right? So this is homegrown only. We have 5 classes: white, 6, out, no action, no ball. These are 5 classes we'll be dealing with. This is our dataset distribution. So roughly we have like 80, 90 some.
I'm speaking.
Yeah, Nitish, can you speak a bit more clearly? I didn't understand what you said about the data set.
Okay. So you have 5 classes in the dataset. We have like gone out and like found these or collected these images by ourselves, mostly from Getty Images only. Right. Cool. So you have 5 classes. You have white, 6, out, no ball, and no action. There's actually a very small problem with here that you can see, but I'll discuss it later. So we have 5 classes only. The data distribution is something like this. We have like roughly 95 or 90 images.
How many images do you have?
So 95. So on it's like 370, right? 370 something. So you have like 370 some training images and like 90 some testing images.
More than 370 actually.
More than
18 to 5 is 400.
More or less 400 training images. I do not know the exact number. So this is roughly like following uniform distribution. So nothing, no like sampling is required here. So we actually next, once we have the data, we do 2 things. Basically, what we do is first we set up our baseline methods to compare our next method that we'll be using, right? So for baseline, what we did is what you call bottom-up approach, right? You first extract the features from the image and then do the classification. So for baseline, we have chosen 3 networks: ResNet 18, DenseNet 161, MobileNet V2. So what we do is we pass the input image, get the features, and do your classification using your regular any class-based loss. This is your baseline. So let's look at some results for the baseline. So MobileNet gives you 86% accuracy just by doing feature extraction, nothing else. Next, ResNet gives you 87% accuracy, and DenseNet for some reason didn't work well and gave only 56 epochs. Notice that this is only for 10 epochs. The training is for 10 epochs, but for ResNet, I know ResNet pretty well. So for ResNet, 10 epochs is more or less, after that, it will start overfitting. So 10 epochs is more or less fine. I presume it's the same for these two. So 10 epochs is a reasonable number of epochs to do for such a small data set. A very like acceptable performance. So once we have set our baseline, what we have constructed is our final pipeline that we'll be working on.
Is it okay if you show the results one more? You just went too fast over.
Actually, Shourjya will explain it with more. Like, so that's his thing to do. Okay, cool. Once we have set up these pipelines, what we these baselines to compare our model against, we'll have our main pipeline. So main pipeline is your bottom-up approach of the same things. So actually, remember, mask CNN is top-down, right? But we have changed this into a bottom-up approach. We are first. So what you do is you take an input image, you use your mask CNN just to calculate your key points. Right? Once you have key points, a key point is a nothing but 17/2 matrix. So you have 17 key points in the image, and each key point is a 2 tuple, which is a 2D coordinate of that particular joint in your image. I'll tell you what all these 17 points correspond to in next slides. Once you have these key points, you pass it through another deep networks and do 5 class classification. Okay, this may seem redundant, but I'll explain you why we do this. So you have 72 by key matrix, right? Now each of this point actually encodes some spatial information in the image, right? Because, so for example, a key point corresponding to nose always has to come up to a key points corresponding to your feeds. Right? So there is some special information encoded in this matrix. Right? And what can you use to make use of a special information? Nothing but your convolution network. You can use any sort of convolution network, but I have some confidence with ResNet, so I use ResNet to extract features from these key points, not from the image. Right? And then using these 17/2 metric to do the 5 class classification. Later we'll see that indeed works. Okay. So is this clear? Should I go ahead? So I presume yes, it is.
Yes, you can go on.
So those 17 points I was talking about are these points. Okay, Shourjya will explain you with more details. So what I was saying, for example, the 2D coordinate corresponding to 0 and 2D coordinate corresponding to 15 has some special information, and this is left, right. So that's why we have used CNN for final classification. These are the results using this. So let's ignore this data augmentation part for now, and we just used mask RCNN to get our 17/2 matrix, followed by your classification. You can see that it works very well because because the way we have planned it, it has to work very well. Compared to 87-83% of your normal accuracy, you have now 94% of accuracy. And mind you, getting from 50 to 70 is easy, but getting from 90 to 95 is not so easy. So this is indeed better than your regular feature extraction. Now the next logical thing to do would be to not use your small data set, but because okay, yeah, right. So we have very small data set, right? So next thing what we do is we use data augmentations to get to basically increase the size of your data set. It doesn't really adds a lot to the performance, but having more data almost always helps, but not in this case, as we'll discuss later. So basically we use three transformations to transform our image. For example, so the three transformations are rotation, shear, and skew. We didn't use flipping. Why didn't we use flip? Because a lot of poses are actually flip invariant, right? So it's like adding redundant data. So that's why we didn't use horizontal flip. So these are the transformations that we did to our data set to get.
No, but that rotation that you're showing, isn't that a reflection actually?
Which one? Okay, this rotation. I think.
Particularly this picture may seem like flipping.
Okay, so I think the torch version of it also does random flipping too. So we use like we didn't write it. It's all provided in the torch. So we just like copy pasted it. It's not. So basically, so what the point that I want to emphasize here is we use data augmentations to change slightly our data set and get to this level. So now we have like 900 images per class, and this is also fairly uniformly distributed. Now we train our mask, the same pipeline with data augmentation, we end up with 92%. So this is 2% less than without data augmentation, and we'll see why. So for that, I'll have to go back, and here you can see that these images, they do not have all 17 points in them, right? For example, these two images have all 17 points, but these do not. So what we are doing, so once you pass these images to our CNN, what you get is maybe 10-12 points which accurately describe this image, and the rest are gibberish only. So what I like honestly do not know why this is happening, but what we hypothesize is that by doing augmentation, you are adding more of these kinds of images to the data set, and these are taxing the model more than what they are supposed to do. This is what our hypothesis is. This is why this is going down. And final experiment that we do is to validate the fact that this 17:2 matrix is indeed have your spatial information. So for this experiment, what we do is we take this 17:2 matrix, we just flat it and pass through a deep neural network. So by flattening it, you're destroying your spatial information. Naturally, it will end up with a bad accuracy, which happens here. So this kind of validates our assumptions that yes, the 17:2 matrix has some spatial information in it. Finally, these are the results, and you can see that ours, whatever pipeline that we have made, ends up with the best result. And that's about it. For next, so any questions about the pipeline?
Yeah, so I just wanted to know what is the sort of literature that you were following for this.
For literature, so this
and
is
when you say ours, that means
it means this is
the data set is yours or the
in the pipeline. This
entire.
also are both of them.
Okay.
And so for literature, we only followed these 4 papers: CNN, RCNN, FastCNN, because this is the baseline. You can not really baseline, but like the base of our pipeline. And this is completely new. We did it ourselves. And this is the final result. And now Shourjya will take you to the code. Let me.
Good morning, ma'am. So we have like 2 different codes. Like first we have the baseline, and then next we have the. No, just a second. Ma'am, can you just give us 1 minute? Just there's some problem.
Yeah, no problem.
Yes, ma'am. Okay. So yeah, we have 2 codes. First, we have the baseline, as Nitish explained, like where we implement the 3 different networks: ResNet, DenseNet, and MobileNet. And then I'll come later to the key points where we do the one we did, like the mask CNN thing. So in the baseline, it's simple. First, we have like so it was a pretty like we use GPU for the whole thing. So that's the thing here, CUDA. So here we import our data set, and we divide it into 2 sets, like train and validation. And then as he already said, we have 5 classes: no action, no ball, out, sixes, and white. Okay, and this is our like the histogram plot, the bar graph plotting of our data set, test data and training data. Just a visualization of what kind of data we use. Like so like you can see this out, 6, no ball, all these kinds of things. Okay, so okay, next we have the okay, so these are all the networks that we have used. Like, so we have ResNet, and then we have DenseNet and MobileNet, and like this is the function we will apply. We will use it later for the training purpose. So here we are. This is the main this is the like training function where we use like all like okay. So we use binary cross entropy loss, and we use Adam optimizer. Okay. Okay. So this is okay. So this is the training part of the thing. So we use so we input the data, and optimizer.0grad, like we set all the values to 0, while in the backpropagation part, like the so while we are in a neural network, the weights the gradients are fulfilled. So when we are repeating the process, we need to empty the thing. So we set all the things to 0 before going for the next loop. So, okay, so this is the printing part of the statistics. It's fine. So, and we are doing 10 epochs for the whole thing. So this is the mobile net thing, the ResNet thing, and the dense net thing. You can see the losses that we have that has come. And here we print our accuracy metrics. So as already you have seen the pictures in the slides. So this is the for mobile net. For no action, we get like pretty good 95.5. For no ball, it's 100. Like yeah, out. So like as you will see, like for example, no ball and out, they can be redundant, like depending on the angle from which the picture of the umpire is taken. In both no ball and out, we like the umpire shows out one arm. Of course, like when we visualize, it's different. One is top, one is in the right. But when it in this case, as we collect the data, there were a lot of pictures where depending on the angle from which the picture was taken, a no ball can be counted as an out and vice versa. So for this reason, you will see like no ball and out are sometimes they have some like the accuracy is a bit messed up. So in case of mobile net, these are the accuracy metrics, and the final is 86%. For ResNet, we have 87%. You can see like same, the no ball and out, the accuracy is a bit messed up. And the dense net, it didn't work so well. So yeah, it has mostly it didn't work so. 56% is pretty bad. So we plotted some outputs for all the three networks that we used, and we printed like the respective outputs that each of the images give after passing through the network. So here there is the mobile net version of the view. You can like it's written, it's no action. This one is no action, no action again. So this one is pretty much not no ball. This is out, as you can see, but our function predicted no ball. That's the problem I just talked about. So yeah, this is for ResNet, the outputs, and this is for DenseNet. And these are the accuracies just to keep it together. So this is our baseline model. Now next we go to our main part. That's the where we use the mask thing, the 17 points thing. So as Nitish already showed you, like the 17, can you go back to the PPT once? Okay, so I'm going to take you to a particular picture. So this picture. So as you can see, these are the 17 points, like nose, left eye, and ear. So there are edges, like, and as Nitish said, there's this spatial information thing that the face always comes above the main body and legs below it, hands left, right, respectively. So these edges help us in maintaining that, like we can't have a edge from nose to the feet without going through the middle part of the body. So to maintain this, we have like these edges. So like 0 to 16 are the 17 key points, and like these are the edges that can exist. Like 0, 1, 0, 2, you will see like here it's like 0, 1, 0, 2, then 1, 3, 2, 4. So these are the edges, that thing. This function is a draw key points function. So basically, like the whole mask thing is like implemented in this function. We basically reshape our, like we take one image, and like this is the function. You will see the implementation like a couple of just after this. So like we take an image and then we like plot the key points on the image, like something like this image will turn into this image basically. Okay, so this is like transforming the image into a tensor. Okay, this is this is like we use the ResNet model for this, like just a ResNet model for like the pre-trained ResNet model, because we will as he showed you in the pipeline, we will be using a ResNet in the end, towards the end. So this is the pre-trained ResNet model. Okay, so and this is like the use of the key point function basically. So as you can see, this is the image that we had, and our function plotted the 17 key points. This is luckily a full image. Like as he said, there might be some problem where we don't get all the 17 key points, but we have like particularly this image, we have like all the 17 key points as you can see, and also a bounding box around the main figure of the image. Okay, so this is like
hello. So I have a question.
Yes,
So
ma'am.
did you have any images that are not front profile, slightly side
Yes,
or 45
yes,
degree side profile?
yes, ma'am. Like yeah, so as you can see, like here only, see, like this is side profile, this is side profile. These are the like output images, right? And there are also images. This is back profile, as you can see, like from the back. There are images where a lot of even the players are in the picture. So in that case, like it will be like the network may or may not predict the correct thing, like as of now. And even there are pictures like I don't think it is in these, but there are pictures like where even the players are lifting the like doing some action with their arms. So like even the network can sometimes even catch the players instead of the umpires. So like those are of course stuff that can be worked on this to improve it better further. Okay, so yeah, this function is a glob function. So basically this function what it does is it takes this image and it converts the converts this picture into the 17 into 2 like matrix that we will later use. Like as in the pipeline he mentioned, after the mask we have the 17/2 matrix which we pass through ResNet to do the final classification. So this is the function that does the 17 like transform the image into the matrix. So we will use this function later. So yes, yeah. So this is the part where we use the function to get the 17 part 17. So the matrix we use the matrix to here. We would divide into test and train, and yeah, okay. And this is like, so still now we were just defining functions. So finally we have like here we import the data like from our basic data. Like remember this is like still we are using the small data set that we collected without any augmentation, without any extra data. So this is the function where we like the training and test function. This is pretty much same as it was in the baseline. It's we use as Adam optimizer and binary cross entropy loss. So this is train and train when we print our like this part is like we measure the corrected levels and the total levels just to plot the confusion matrix later. So this is the second part of the output that Nitish already showed you. This is like without augmentation. We, as I said already, Adam optimizer and binary cross entropy loss. So this we do the whole thing, and finally we have this matrix. So you can see it worked pretty well. We have 94% accuracy with like total accuracy with in 2 cases and above 90% in the other 2 cases. This is the second part, and finally the third part is we do the augmentation of the data. We include the 3 rotation, shear, and skew. But as I already said, like there might be a lot of redundancies, and there are pictures that does not show the complete 17 key points. So sorry, we might face some problem like some decrease in accuracy due to that. And so after augmentation, this is the data set. You already have seen the graph before. So we have approx 900 data for each class. So yeah, total approx about 4,500. Here we train the data for this after augmentation, the training part. You see the whole loss. This is the losses we had after. Yeah, and now this is the like plotting the results. And this is like you can see it's also pretty good compared to the baseline thing, but yeah, the accuracy did decrease by 2% compared to without augmentation. But you see, like we like in a machine learning problem, just with 400 or 500 data, it's not enough. Like it can like basically underfit a lot. So we need a lot of data. So yeah, like yeah. So augmentation was necessary, but we need like proper good quality images with all the 6 or 17 key points for all the images. Maybe augmentation to that will not result in decrease in accuracy. And this is the linear layer part, like where we validate the fact that the spatial information is necessary for this classification, this particular classification. So basically we just flatten out the 17 into 2 thing into a 34 vector, like 34 into 1 vector. And again, the same thing, we use binary cross entropy loss and Adam optimizer to do the thing. And yeah, finally we have this matrix. It is, yeah, it performed pretty bad. You see 75% with like literally no ball is 0. It did not even predict 1 correct. So this was the pretty much thing, but as like there are quite a number of drawbacks which can be worked on and improved to draw this project better. So firstly, basic thing, we had very little data. Like we collected approx 450, we handpicked 450 data, which was still pretty less. Like we could not find more images on the web, probably. Yeah, we could not find more images on the web, like images that can be actually used for this purpose. And also the images we collected, as I already said, some are half, some are full. And like, for example, like a site post half image will have like very few key points that can be obtained from that picture. So yeah, and another problem is we just discussed 5 classes basically, but as you might know that they're implicate, we can have like a lot of other actions like for and like leg buys. But the problem with those are like moving actions, like 4th ampere moves his hand, or even leg buy, or even 3rd ampere. So we those are like a complete different like a way to improvise this complete idea on. And there also we might face another problem, like why can't we use like the images of those things? Because like for Ford and Noble, there can be a huge redundancy because it's like moving one arm. So there's a very high chance that the classifier will misclassify the Ford and Noble thing. And same will go for the 3rd ampere and 6th thing, because in the 3rd ampere action, there is a particular moment where the arm smile looks like it's a 6. So unless we like come up with something better, this redundancy can also cause a problem. So yeah, these are the few improvisations that can be done on this idea, and that's it. Thank you, ma'am. Any questions?
Yeah, I have one question. So the images you said you took from the internet. Did you do any kind of pre-processing in the sense that these will be mixed size, mixed resolution images? Did you try to uniformize them in any way?
So ma'am, we like maintain the fact that like all the images are like 300 into 300 resolution, so not less than that, because it will become too easy. And
so the images that were collected were variable resolution. So what we did is we first resized them to a bigger size, 505, and then we center cropped it, because most of the action is happening inside the very little portion in the image. So basically at the end we have like 300 by 300 square images. That's all. This is the kind of pre-processing, because we are dealing with the shape of the object, not really the quality or anything like that in the image. So no, not a lot of pre-processing, except the fact that the umpire in the image is at the right position is required. So that's
okay. Yeah, thanks. So there is I have one more question, one last question. So did you notice that did you have any observations about how the background, suppose the umpire is wearing white and is on the back standing with a background of white, did that affect?
No, not really. Yes, you do the normalization, so these things they go away. Plus, so how the RCNN is trained for key point estimation is that you have masks that have one at the location where it is where that joint is located, and 0 everywhere else. And what you do is you pass the image, you find the RCNN would output your mask, and you'll do binary cross entropy loss pixel wise with those masks. So there's nowhere in that model that they take the model looks at color of the image or the shape of the image or anything like that. It is only interested in the contour, not contour, but rather the shape of the umpire present in that image. That's all.
So shape wise only. So to determine the shape, for example, it will look at pixel changes, no?
Right.
So that in that sense, I was asking if the background color and the shirt color, maybe if it's the same, does it have difficulties recognizing the contours?
Then it will happen.
Yeah, so I just wanted to ask if, in your results, if you have seen such a misdetection because of this issue.
So, like, as we handpicked the data, like I don't like, we don't recall, I personally don't recall like there was like any, I mean, we took pictures from the web, so like
No.
pictures.
She's asking if
Yeah, I know.
background and foreground
Also
are the same
white and
color.
the exactly like
I think there will be problem. We'll look for it. If we can find any such sample, we'll pass it through and see what it plots.
Yeah, okay. Thanks. All right, so does anybody in the audience have questions? All right, it doesn't seem to be the case. Okay, I would like to thank Shourjya and Nitish. This was a very good talk and also a very good subject area for sports applications. So yeah, so thank you for the talk and we'll meet again in 15 minutes.
Thank you, ma'am.